And now, to have a look at the mysteries of Europa, is Dr. Robert Pappalardo with the Jet Propulsion Laboratory. He is the current project scientist for the Cassini mission. Let's welcome Bob.
Okay. All right. Thank you very much. We're here to discuss challenging the paradigm and changing paradigms. So rather than present a talk on what we know about Europa, I want to present a talk on what we don't know about Europa. Arguably, we're in our understanding of Europa about where understanding of Earth geology was prior to the plate tectonic revolution. We understand feature types. We have some ideas of how they form. We have some ideas of composition and how Europa works overall. But we have to expect that when we investigate Europa more closely in the future with an orbiting spacecraft, that a lot of those things that we think we know, we'll learn that we didn't know so well. And there'll be new questions, of course, and new issues that arise. Now, Europa 400 years ago helped bring about the Copernican revolution with Galileo's observations of Europa and the other satellites that bear his name. And it's fun to put Galileo's sketches side by side by date with where we can go simulate with the JPL Solar System Simulator, where we could go back in time to Padua at about 7 o'clock in the evening and try to match up the satellites to his observations, and that we can see on that first fateful night in January on the 7th in 1610, Galileo essentially saw all four, but Io and Europa right on top of each other merged into one. And it took days before it was apparent that these were four distinct objects traveling about Jupiter. 400 years later, the Galileo spacecraft, as Torrance reviewed, has explored these large satellites, given us a much better understanding of the processes there, showed us that Jupiter is somewhat like a miniature solar system, where Europa essentially holds the position analogous to Earth in the inner solar system. Not too warm and tidally heated as Io is, and not too cold and receiving less tidal heat, less tidal energy as Ganymede is, but holds a position where it can have some H2O and receive a reasonable amount of tidal heating, enough, we think, to maintain a subsurface ocean within. Looking at Europa's surface stretched out into map projection shows it's unlike a typical satellite like our moon. It's not covered with craters. In fact, there are very few. Here's one, Pwyll, or Pwch, if you're Welsh. And here's one more, but very few. These are not impacts, but instead modeled terrain from internal processes. Overall, Europa is split into, first, its ridged plains, the bright regions, where zooming in shows the surface is crisscrossed by a myriad of features. Many of them ridges, these kind of double ridges with an axial valley, and some broader bands of material that crisscross the surface, apparently generations of them. Superimposed on that, in general, newer terrain is the modeled terrain, which has destroyed the ridged plains in situ. You can see the ridged plains here have just apparently disintegrated in place and replaced by this more chaotic modeled terrain. Again, very few impact craters. A lot of the smaller ones are secondaries from the larger craters. So few craters that based on telescopic observations that estimate the number of kilometer-scale impactors that are out there now, the surface, based on roughly the number of craters that we can observe, is about 60 million years old, which is just a blink of an eye geologically. In about 1% of the age of the solar system, this last percent, Europa's surface has been completely repaved, destroying the craters that were there previously. Torrance Johnson touched on the best reason to believe that there is an internal ocean within Europa today. Theoretical models say it could be there. The geology says it was probably there. The magnetic field data, the induced magnetic field, suggests it is there today. And again, as Torrance alluded to, and as Dave Stevenson discussed as well, the magnetic dipole of Jupiter is tilted by 10 degrees. The magnetic equator is somewhat mapped out here by the Io torus in this illustration. And Europa and the other satellites traveling along are moving slowly compared to the rate at which Jupiter is rotating around every 10 hours. And so, because of the dipole tilt, they find themselves first above the magnetic equator and then below the magnetic equator. Europa is feeling this change of the Jupiter field on a 5.5 hour time frame. And what the Galileo spacecraft measured is that Europa is inducing its own magnetic field to counter that external changing Jovian field, implying that it's behaving as a conductor with a material that may be that salty, presumed salty ocean, as shallow as 15 to a few tens of kilometers below the surface. Now, Europa, as it orbits around Jupiter, is breathing in and out, we believe. If there is, in fact, a decoupling ocean between the interior and the outer icy shell, then Europa's surface should rise and fall by a total of 30 meters every time it orbits around Jupiter, being stretched out more as it's closer to Jupiter and contracting somewhat as it's further away. You can also see Jupiter seeming to move back and forth in the sky because we're traveling along with Europa in this simulation, not to scale. And Europa is rocking back and forth or librating relative to Jupiter. So it seems like Jupiter is moving back and forth in the sky, simply a result of Kepler's laws as Europa orbits around, nodding with respect to Jupiter and facing the empty focus in its orbit. It's this tidal flexing which generates the heat to maintain Europa's ocean. Most of it, we believe, is probably deposited in the ice shell of Europa. Where the ice is warmest is where the heat will be dissipated. It is possible, if the mantle is hot, that heat is also dissipated there, but that's one of the unknowns. Again, as Torrance alluded to in showing this slide, we're now understanding that oceans may exist in many large icy satellites, and maybe even in some small icy satellites, Enceladus in particular. The Galileo spacecraft was able to perform the magnetic experiment at Callisto, which somewhat surprisingly shows evidence for a salty ocean. Ganymede hints at it through its intrinsic dipole magnetic field. Titan, based on largely based on its obliquity, is hinting that there may be a subsurface ocean within. And Enceladus, based on its chemistry and its thermal output, is hinting of liquid water within. The one of these things that doesn't belong here is really the Earth, that is so different in having its ocean on the outside, whereas Europa and the other large icy satellites are teaching us that internal oceans may be the most common type of ocean, not just in our solar system, but in the universe. Therefore, if these are potentially habitable environments, then these may be the most common habitable types of habitable environment that exists. Europa's is the most compelling in this way because its ocean is probably in direct contact with its rocky mantle. The icy shell is thinner than other deeper oceans in the larger icy satellites. So I'd like to pose in the next slides 12 questions that I think will contribute to changing our notion of what we think we understand about Europa today as future exploration of Europa and other icy satellites proceeds. A top question is, what is the three-dimensional character of that icy shell? There are really two end members that have been argued based on the geology of Europa. One in which the ice shell is very thin, just a few kilometers thick, thin enough that it can crack all the way through to create outbursts and build ridges through slushy material coming up to the surface, build bands by opening up and exposing seawater, which freezes, and creates chaos regions, and we'll look at all these close up in the coming slides, through direct melting of that ice shell, which would imply a very high output from that rocky mantle. Would imply extreme tidal heating of that mantle, and in fact a lot less or negligible amounts in the ice shell. The other end member suggests a thicker ice shell, tens of kilometers thick, in which convection operates, bringing warm icy material from the bottom of the ice shell toward the top. There may be melting within that ice shell triggered by tidal heating or by low melting point temperature contaminants, and implies lesser or even negligible mantle activity. These end member models have different implications for habitability and even for future exploration, whether an ocean can be in direct contact with the surface, as in this model, or in indirect contact with the surface through convection through convection of the ice shell. And understanding the processes by which the ocean and the surface could potentially exchange material is really key to the issue of whether Europa could be a habitable environment, as we'll come back to. What are the mechanisms of icy shell cracking? There are evidence for troughs across the surface, troughs that seem to build into ridges. There are limited mechanisms for generating stress in Europa's ice shell, yet it seems that Europa's ice shell can crack. Whether it can crack all the way down through an ice shell is in question, and how the stressing mechanisms can create cracking is a question. An important contribution to understanding these issues is observations of cycloidal features on Europa's surface, these bizarre chains of arcs that cross the surface of Europa. These were first observed by Voyager, observed with wider distribution and more closely with Galileo spacecraft imaging. And it took Randy Tufts and Greg Hoppe until they studied this idea of the orbital stressing of Europa, as we saw in that illustration, the combination of a radial tide plus a librational tide, to realize that if a fracture propagates at just the right speed across Europa's surface, it can follow the changing direction and magnitude of stress across the surface to create an arc. So if you were standing on Europa's surface, the stresses would rotate and change in magnitude around you during Europa's day, its orbit around Jupiter. And a fracture propagating at the oddly slow speed of about the speed a person can walk would be able to follow that changing stress direction and trace out an arc across the surface. We don't really understand why, if this model is correct, why the effective speed of fracture propagation would be so slow across the surface. Again, whether such fractures can penetrate deeply enough to really affect the surface. There are a lot of questions related to the mechanisms of ice shell cracking, but this elegant model starts getting at these issues. what is the rotation history recorded in the icy shell? There has been a lot of discussion about whether Europa undergoes non-synchronous rotation. That is, the ice shell is predicted to get a slightly extra spin up, a little extra torque near perigove when it's closest to Jupiter. And that should cause the ice shell, if it's decoupled from the interior, to rotate slightly faster than synchronous. Now, very unlike the orbital stresses, which are acting on the 3.5-day orbital period of Europa, this is predicted to act on a time scale of something like 10 to the 7th years for one rotation, but nonetheless can build significant stresses in Europa's ice shell, even more than those orbital stresses. Previous workers have shown that the global scale pattern of Europa's lineaments is a pretty good match to the tensile stresses predicted if the ice shell is indeed slowly slipping relative to the interior. Now, some recent results by my graduate student Zane Selvins, who will defend tomorrow and tell us about these results, is that actually any lineament on Europa's surface, if you allow Europa's shell to rotate at as much as you'd like, can fit somewhere. It's not so much the goodness of fit of the global pattern that matters, but what he's finding is that overall the fit is best if you back rotate Europa about 30 degrees in longitude, implying there was a spike, a peak in the formation history of Europa about 30 degrees ago. So that's actually better evidence for non-synchronous rotation than just the fact that the lineaments will fit with some back rotation of Europa's ice shell. So indirect evidence for an ocean. But there are other things that can induce reorientations of Europa's ice shell as well. The thickness of the Europa's ice shell, as in this plot from Ojikongas and Stevenson from back in '89 or so, predicts that Europa's ice shell, simply because it's much colder at the poles, should be very thick at the poles. There are also thickness variations across the equator. But that thicker ice shell in the poles could cause true polar wander, could cause Europa to literally flip over due to the ice shell thickness variations. And recently, Schenck and others have argued that specific tectonic features, the long arcuate depressions on Europa, fit with the predictions of the stresses generated from true polar wander, from flipping over of Europa. And so really the rotation history, putting together the story in Europa's crisscrossing lineaments is really just getting started as an occupation. And once we have global coverage of Europa and can put together that pickup sticks story instead of just isolated regions where we can do it now, we'll be able to put together, hopefully, this very complicated rotational history of Europa's ice shell. Ridges are about the most ubiquitous feature on the surface, yet we don't really understand how they form. There have been a whole range of models suggested: volcanism, tidal pumping, diapirism, compression, wedging meaning essentially diking, pushing up the surface. The most comprehensive model, I think, and probably the one the community is leading toward, is one of shear heating, where fractures penetrate through the top cold, brittle surface layer of Europa. And once they do, these stresses, again, that are rotating around during Europa's day, cause each side of that fracture to move back and forth during Europa's day, to slide back and forth. Imagine if the San Andreas Fault, instead of always headed one direction, were moving back and forth by tens of centimeters on the time scale of 3.5 Earth days. That's what we think would be going on Europa's fractures, enough to generate heat along the fracture, that heat warming up the ice on either side, that buoyant ice rising up just slightly, enough to push the surface up into a ridge, or to create a weak zone that allows for compression to concentrate and form a ridge. So an elegant model that combines the tidal stressing, cracking, strike-slip motion that's predicted. But again, until we get there and really map out the morphology of the ridges, understand their history in the stratigraphy, and ideally with radar, understand the plumbing of ridges where we understand what forms them and how liquid water is involved, if at all. Chaos regions, aptly named, where blocks have broken off of the ridge terrain, have translated and rotated in a hummocky matrix material. Some appear to have tilted as well. The two end-member models here was there melt-through of the ice shell to form these chaos zones? They look a lot like Arctic sea ice, but is that plausible? The amount of energy needed is large, and the ice shell will tend to flow and fill in a hole if it's melted out, unless the ice shell is relatively thin, just kilometers thick. Or in a thicker ice shell model is warm ice, individual diapirs or concentrated tidal heating, causing partial melting of a salty layer to melt out chaos zones and allow blocks to translate like on the top of a mosh pit. That leads to the issue of, is the icy shell convecting? There are pits, spots, domes on Europa's surface at kind of the 10-kilometer scale. Here are some closer up. This looks like it's been pushed up. The light's coming from the right. Here, a little mini chaos zone where the surface has been replaced. Is that, as in this cartoon, related to the rise of warm ice diapirs toward the surface? In convection models like this one by Amy Barr, plumes can rise from the ice-ocean interface toward the surface in something like 10 to the 5th years, but it's very difficult to break through the very cold, stagnant lid nearer the surface, the top third or so. So it might take compositional variations or concentrated tidal heating to get those blobs of warm ice up to the surface. So is Europa's ice shell in fact convecting to form these features? Is it happening today? Is it broad across the surface, or is it in just isolated regions that convection is ongoing? What are the non-ice components of the icy shell? Well, from infrared spectroscopy by Galileo, we know that there's some non-ice material with asymmetric, relatively shallow absorption bands at 1.5 and 2 microns. Brad Dalton has compared those to various salts that have been suggested on Europa's surface, looking at cryogenic temperatures. In general, it seems that hydrated salts, such as magnesium sulfate hydrate and sulfuric acid hydrate, which may be made on the surface from processing by irradiation of surface materials, may explain the infrared signal, and maybe chains of sulfur could explain the reddish color. But we need to really understand, using better techniques, higher spatial and spectral resolution, what this red dark stuff is. With a mass spectrometer in orbit, one can take a speculated surface composition and predict what would be seen. So with a mass spectrometer in orbit, we can get at Europa's surface composition, because the surface conveniently comes up to the atmosphere through sputtering of the surface by radiation, hitting the surface, knocking particles up 100 kilometers or so. How active is Europa today? We expect from tidal kneading that Europa's surface is probably cracking and shifting and active today, but we don't know that for sure. We haven't been able to look with Galileo at the same regions compared to Voyager at high enough resolution to see changes. There's certainly a lack of change at 2 kilometer per pixel scale between Voyager images and Galileo images. Higher resolution data didn't cross so well, and so it's much more difficult to look for high-resolution changes. That consistent, though, lack of change at 2 kilometers is consistent with its tens of millions of years surface age. Is the rocky mantle hot? Bill Moore has done some work showing that the interior of Europa should be in one of 2 stable states, its temperature versus its heat flux. looking at that, he's shown that there's one stable state where radiogenic heating alone maintains the heat flux out of the rocky mantle, in which case Europa is cold and essentially dead in its interior and moon-like. The other end member, Europa's mantle, may be hot and tidally heated and Io-like. Those are the two stable states. So which is it? One is much more attractive for things like hydrothermal vents and life within Europa, and the other isn't so much. Or might Europa be able to shift, although it can't get out of one of those states, might it be able to shift back and forth around some unstable equilibrium state instead and have a modestly warm mantle, or one that undergoes changes through time? Has Europa's activity changed through time? Geologic mapping suggests that chaos regions are generally newer than the ridged plains. That's strange that Europa's surface would have gone through some transition in its geology in the last 1% of geological time. So maybe it's a coincidence and Europa just died out and went through a chaos-forming event, a convection event, or warmed up. But perhaps instead, its orbit is known to be coupled to Ios and to Ganymedes. Ios has been predicted to go through periods of changing eccentricity, which would pull Europa along with it on timescales of something like 100 million years. So Europa's ice shell thickness may even vary from something like 15 to something like 35 or 45 kilometers thick through time. We may be in a waning phase of geological activity where Europa's shell has thickened up, convection kicked in, and now Europa is relatively inactive, waiting to wake up again 50 or 100 million years hence. How does Europa couple to the external environment? Again, we've talked about radiation being key to modifying the surface. Europa is not in isolation. It receives some of its material from Io, which would stain its surface. Understanding the coupling of the surface, the atmosphere, and the magnetosphere is also key. And finally, the big question, is Europa's ocean habitable, and for that matter, is it inhabited? Irradiation of the surface ice creates oxidants. Can those oxidants get into the surface ocean? It depends on the resurfacing mechanisms, which we don't really understand. Is its mantle hot enough that there is hydrothermal circulation and production of reductants on the ocean floor? If such reductants and oxidants got together, then there are great fuels for organisms within Europa's ocean. But we don't understand the processes, the exchange processes, well enough to know. These are the kinds of questions that will be addressed by the Jupiter-Europa orbiter, which is in its planning stages, has objectives related to ocean, ice shell, composition, geology, and the Jupiter system as a whole. But as I was alluding to, it's going to change our current paradigm, but certainly leave many questions unanswered. As we get toward understanding the nature of Europa's ocean and its potential habitability, and understanding whether Europa might, and someday hopefully understanding if it does, actually contain life, then just like 400 years ago, Europa may contribute to changing a very large paradigm, one which asks the question, are we alone in the universe? Thank you very much.
Let us take one question. Then
All right.
thank you, Bob.
Thank
again.
you.